This is a video of 3-3 on rotational momentum. We're doing problem number 17. My family is in the background, but I think that they should be far away enough to the point where you can't hear them. It's mainly my brother. Okay, so I'll start reading. A space station is constructed in the shape of a hollow ring of mass for 4.8 times 10 to the fourth kilogram. Members of the crew walk on a deck formed by the inner surface of the outer cylindrical wall of the ring with a radius 145 meter. At rest, when constructed, the ring is set rotating about its axis, so the people inside, effective free fall, acceleration equal to g. So I believe when they say like at rest when constructed, they mean like moving at a constant speed, or rather rotating at a constant speed. The rotation is achieved by firing two small rockets attached tangentially to opposite points on the rim of the ring. So problem A asks, what angular momentum does the space station acquire? So I went ahead and, what do you want to say? I drew a top-down view of the space station. So there's our radius. We have the mass radius. And then by this, what do they call it? They called it free fall acceleration equal to g. By that they mean the centripetal acceleration. I was a little confused, but I remember the movie Interstellar, where the characters, they're flying through space in the ship and it has the ring rotating around it. And I believe that's to generate some sort of gravitational field. Maybe we'll learn about that later. But anyways, centripetal acceleration equals g. And also the Hoops moment of inertia is mr squared. Problem A asks us to find angular momentum, which is L. I wrote down, two equations that we know, which is L equals I omega and L equals R cross P. And there's no reason to write the elastic or inelastic equations because this is just one object really rotating. And what am I trying to say? Yeah, it's just one object rotating. There's no like locking hands or any of that. So and for W, we'll be able to find W using this AC equals V squared over R equals omega squared over R equation. So yeah, let's go ahead and do that. And then so obviously we have AC, which is G. That's a given. And then omega squared we don't have, but R we do have. So plug in those two values, set it equal to omega, and then angular speed equals 0.26 radians per second. And then so we now have our omega and our moment of inertia we always had. Go ahead and plug in the values, and then get a real big number. I have to do the scientific notation, and remember how many zeros or how many the exponent of the time I have to do the skipping. So then you get 2.6 times 10 to the 8 kilogram meters squared per second, which is our momentum. And then if I look at part B asks, for what time interval must the rockets be fired if each exerts a thrust of 130 newtons? So we have the Fn of the rockets, and obviously they are both 145 meters from the center. Torque equals F, should be F cross R, because we don't know, or the formula is in such a way that we don't know if the forces are exactly perpendicular to the rotation. Anyways, two torques of the same magnitude, and they're both assisting. They're both assisting the rotation, same direction. I guess I named it counterclockwise, so they're both going counterclockwise. And so we just plug in our F and R, and we get 37,700 Newton meters. And from there we go, torque equals angular momentum over time, plug in two values, solve for t, 6,897 seconds, and then we plug it first answer into the website, all good, second answer into the website, all good. And here's my takeaways. It's a rather simple angular momentum problem. You don't really need angular momentum bar graph or anything because, again, it's just one object rotating, pretty simple. And some interesting part I found is that you don't even need to use angular momentum in part B. Let me explain that. So after I found my torque, this is what I originally did because I thought, oh, you can use angular momentum, just torque equals I alpha, and then from that use a kinematic equation. So I did that. I found the angular acceleration. I plugged into the kinematic. We know we end at our final angular velocity is, omega, or is 0.26 radians per second, initial zero. And then from that, I actually got a more accurate answer compared to this one. Because on the website, it's 6,960. And then, this is definitely within 10% of that answer, but it's just interesting how when you use the kinematic equation, it's more accurate. And I mean, that's just an interesting part. Obviously, this is the angular momentum video, so I should be using angular momentum, but nevertheless, it's just, something interesting, and it's kind of nice that in physics, there's multiple ways to go about things. And I also just put, hey, is this, a little tease for gravitation because I thought that was fun. So yeah, takeaway is pretty simple problem. I was able to knock it out pretty quickly. Thank you for watching.